Sorry, I think it's lost the connection in between. Uh, some issues with the technology. So we are extremely grateful to Professor Martin for agreeing to deliver this talk. He has been a pioneer in this field in Antarctic science, and it's really we are extremely grateful for agreeing to deliver this for this as a part of the Krishnanunni Memorial Lecture series. I'm very happy to introduce, of course, I know he doesn't need any introduce to the Antarctic community, but still we have a lot of the people who also join. I would be very happy to introduce him. Professor Martin Siegert has been co-director of the Grantham Institute since mid-2014. And before that, he was director of Bristol Glaciology Center at Bristol University, where currently he is visiting professor and head of School of Geoscience at Edinburgh University, and where he holds an honorary professorship. So he has been widely known in the academic circle, and because of his expertise, he has been honorary and visiting professors in many universities. He also led the Lake Ellsworth Consortium, a UK NERC funded program that designed an experiment to explore a large subglacial lake beneath the ice of West Antarctica. He has undertaken 3 Antarctic field seasons using geophysics to measure subglacial landscape and to understand what it tells us about the past changes in Antarctica and elsewhere. And in 2013, he was awarded the Martha T. Buse Prize for Excellence in Antarctic Science and Policy, one of the highest award anybody can get in Antarctic science. And in 2007, he was elected as a Fellow of Royal Society of Edinburgh. So with these few words, and very recently there was a news that one subglacial lake vanished within 6 days or something like that. I'm sure that Professor Martin will throw some light on that aspect as well. And with this few words, Professor Martin, floor is yours. Please go ahead.
Many thanks, and thank you everybody for your time today. It's a pleasure to be here and honour to speak to you. I'm going to share my screen, I hope, and you should be able to see that. Can you just give me a thumbs up if you can see my my presentation? Oh, I can't see anybody. Just can someone tell me that you can see it?
It's
yep,
seen.
good. Yep, perfect. Thank you very much. Okay, so why is Antarctica changing and why should we care? That's the title of my talk to you today. So this is me. I'm on the edge of the West Antarctic ice sheet, the beautiful Patriot Hills in the background, and the ice beneath me is about 600 or so meters thick. Now, the work that I do, as Naresh Pant, who's with us today, knows, we're working collaboratively on some things, is that I use geophysics to try and peer underneath the ice in Antarctica. And one thing that we use is an aircraft. This is a DC-3 aircraft, and you can see underneath each of the wings there are antennas. One is an antenna emitting very high frequency radio waves. The other antenna is receiving it. Radio waves travel through cold ice as if it's not there, but they bounce off the bottom of the ice sheet. And so you can determine and measure the bottom of the ice sheet by the radio wave reflections. And this aircraft can fly around Antarctica and you can get lots of data very quickly. And we've been using this technique for several decades now to chart and map what's underneath the ice. So that's my contribution to Antarctica. But my story is going to go back to the Swiss Alps and back in time to the 19th century. So this is the Aletsch Gletscher in the Swiss Alps, beautiful glacier, one of the first glaciers to ever be studied scientifically. And the early people that were looking at this, people like Louis Agassiz, were questioning why this valley has a glacier in it, and this valley, which isn't so far away, just doesn't. It's further down slope. So this is, I'm looking down at the village of Zermatt here in the Swiss Alps. This is a holiday photograph, by the way. There's a couple of holiday photographs for you in my lecture. What's the explanation? What is the explanation for why this valley doesn't have a glacier, oops, and this valley does, when actually seemingly, from looking at the sides of the valley, it's pretty similar? And the reason is, of course, this valley did once have a glacier in it. And Louis Agassiz saw that and understood it and came to his theory, which was that the world had once experienced a lot more ice on the planet than it does today, so-called glacial theory. And of course, one logical outcome of glacial theory is that the world has warmed since the Ice Age, and all that ice has been lost. And of course, in a warming world that we have today, that type of thinking is completely relevant. I mean, it's a beautiful place just north of Zermatt. This is looking over at the Matterhorn, another one of my holiday photographs. There is a lot of action going on in this image here. But one thing I want to point out to you, this is a glacier at the moment, and you can see there's a trim line just here. This is very quite well weathered rock over here and exposed rock underneath. This glacier has melted a lot in the last 100 or so years. Not just this glacier, but glaciers all over the Alps and all over mountainous glaciated environments like the Himalaya, obviously, but all of the glaciated regions as well. Now, 19th century naturalists and scientists were quite taken with glacial theory, and they wanted to understand whether there was evidence for it in other places. So this is in North Wales, in the United Kingdom, a place called Cwm Idwal, which is a very famous spot. Charles Darwin visited this place twice. The first time he went, he really didn't understand the idea of glacial theory. He was expecting to see evidence of glacial theory, but he couldn't really see any. Then he went with some other people who have been there before and recognized what they were looking at. And it's these hummocky hills over here and over here, which we now obviously know are moraine features. These are hills and hummocks that were deposited by sediment in a glacier that is no longer there. This is a classic glacially overdeepened trough, of course. And Charles Darwin suddenly understood glacial theory from his second visit to this site. And by the cafe at Cwm Idwal, there is a Welsh slate with this beautiful inscription of a quote from Charles Darwin, and I'll read it out to you. Neither of us saw a trace of the wonderful glacial phenomena around us. A house burned down by fire did not tell its story more plainly than did this valley. It's a beautiful comment. Basically, there's nothing greater in science than admitting that you're wrong. And that's what Charles Darwin was doing in this quote, that he just couldn't see it to start with. And then obviously when it was pointed out to him, it was so clear. And glacial theory, actually, the evidence for it is all around us in many places. This is a part of England, a county called Suffolk, and it was where I was brought up. I wasn't brought up in this beautiful house, by the way, but nonetheless, I was kind of brought up as a child here, and I thought this landscape is pretty boring. There's not much going on. It's all flat. It's full of sediment. But actually, this sediment and these hills were all deposited by ice. Not the last ice age, not the one before that, or the one before that, or even the one before that, but the one before that one, about 500,000 years ago, called the Anglian glaciation, because it absolutely covered the whole of East Anglia. That caused the landscape that we know so well today. The Anglian glaciation is really interesting, actually, because it was the largest glaciation to affect the United Kingdom. Ice got as far south as just north of London, and it punched a hole through some hills just north of London, a place called the Chilterns, and the River Thames that had previously flowed out toward the Suffolk coast went south, diverted through the Chiltern Hills, and came out to what we now know as London. So, we take the world around us for granted, but a lot of things in our world have been given to us, directed to us from processes that have been natural processes that have been going on the planet for tens of thousands, sometimes millions of years. And we shouldn't forget that there is a connection between our world and what has happened before us. And that is particularly relevant when we start thinking about climate change, because in years to come, there will be a connection in the future world to what we are doing to the planet today. And we absolutely know that by studying places like this. So let's try to explain glacial theory. Now we know that it happens and ice ages happen. How do we actually prove it and explain it? And two people came up with ideas that were completely true, but they died without anybody really understanding that they were correct. One was James Kroll, a self-taught Glaswegian scholar, and another was a Serbian mathematician called Milutin Milankovic. They each came up with the idea that ice ages can be explained by the way that the Earth orbits the Sun. Sometimes it's slightly closer, sometimes it's slightly further away, sometimes the Earth is tilted more, sometimes it's tilted less. There's a number of other processes that are going on, and all those relate to the amount of solar radiation that comes onto the planet's surface or not. Sometimes it's slightly less, sometimes it's slightly more. And what these two concluded was when it was slightly less, when the solar radiation on the planet was slightly less, by virtue of the way the Earth rotates around the Sun, then you have an ice age. And when it's slightly more, then you have what's called an interglacial. And initially, these ideas were heralded as the explanation for glacial theory. But it was pointed out on both occasions that the amount of change that can be invoked by the orbital variation is tiny. It's just a few percentage points different between the maximum amount of solar radiation and the minimum amount. And it's just not enough to cause massive changes to the world that we know happens in an ice age. So we need some other process to take effect. So it'd be fantastic if we had a time machine and we could go backwards in time to the ice age 20,000 years ago, and maybe ice ages before then, so we can actually measure the atmosphere around us. Or if I can ask everyone to mute themselves, if everyone can just put themselves on mute, that would be great.
Director sign. Head of the facilities.
Can everyone put themselves on mute, please?
Please mute yourself. Please.
Hostel address. Institute.
There's someone's talking.
Please mute yourself.
Thank you. Okay. So it would be great if we had a time machine. We can go back in time. And that's exactly what we do have. It's called the Antarctic ice sheet. Now, I told you that the edge of the Antarctic ice sheet, where I was, around about here, the ice thickness is about 600 meters. But if you go to the middle of the East Antarctic ice sheet at Vostok Station, coldest place on Earth, by the way, the coldest temperature ever recorded was at Vostok Station at minus 89 degrees centigrade. The ice thickness here is 3,741 meters thick. But the accumulation rate of ice, the amount of ice that accumulates every year on the surface of the ice sheet, is only about 1.5 centimeters. So think how long it takes if you're accumulating only 1.5 centimeters to build an ice sheet that big. It takes millions of years, and that's why the ice in Antarctica underneath the surface is so old. Now, what you could do, of course, is you can go to this place and you could set up a drill rig. This is the Russian Vostok Ice Core facility, and you can core the ice out from the surface down to the bottom, and you can take a very thin section of that ice and it will contain air bubbles. Now, those air bubbles are a sample of the atmosphere at the time that the ice around it was previously snow. It's a time capsule, and you can essentially take that air bubble, put it into a laboratory, measure the atmospheric composition of gases at the ice age, the one before that, etc., and you can completely measure the changes in the greenhouse gas concentrations in our atmosphere during those times. And this is what this graph does. This is time on the x-axis. Here we are today to 400,000 years ago, and this is carbon dioxide in parts per million. And you can see there's an oscillation going on here, where the carbon dioxide value goes from 280 parts per million down to about 180 parts per million, and then it comes up again and down again, really regular, 280, 180. This is the last time over here that we had an interglacial between ice ages, and carbon dioxide value was 280 parts per million. This down here is the last ice age, when the carbon dioxide was 180 parts per million. And then 10,000 years, we came out to, again, 280 parts per million. This pattern matches precisely with the orbital variations. And what it tells us is that Kroll and Milankovitch were correct. The ice sheets are being paced by the way the Earth orbits around the sun. But the amplification factor that's so important is that these small changes in solar inputs cause large changes to carbon dioxide value on the planet. And I say large changes, we're talking about 100 parts per million. And that is enough. That is enough over hundreds and thousands of years to cause global cooling of 5 or 6 degrees centigrade and the big ice sheets to build up. And then in reverse, global warming of 5 or 6 degrees centigrade and the big ice sheets to decay again. So here we were in about 10,000 years ago, and then 1850 or so, 1950, and here we are today at over 400 parts per million. So way above the amount of carbon dioxide that's in the atmosphere for the last 500,000 or so years. We can take a nearby ice core, Dome C, even further back to nearly 800,000 years ago, and you can see the same type of patterns. The Anglian glaciation that I referred to previously is this one over here, by the way, at 440,000 years ago. Then there was an interglacial, another ice age, an interglacial, another ice age, an interglacial, another ice age, an interglacial, the last ice age, and here we are back today. Now, let's think about the last 1,000 years. There is a lot of clutter in this graph. Again, time on the y-axis, last 1,000 years, average surface temperature on the planet in the x-axis. If anything, there's been a bit of cooling going on for the last 1,000 or so years until around about 1850, and then we get a lot of warming, this sort of 1 degree of post-industrial warming. We can match that surface temperature graph with the carbon dioxide concentrations on the planet, and you can see there's like a 1-to-1 relationship, that carbon dioxide levels are going up and air temperature is going up, and that's because there's a causal influence going on here. We've been measuring carbon dioxide actually for many years, very accurately from the Mauna Loa Observatory in Hawaii, and this is the last 50 or so years, 60 or so years of that record, and there's a number of things to take notice of this. The first is that the red line is the measurements. There's an annual oscillation here going on, and that's because in the northern hemisphere in the summertime, like now, there's a lot of vegetation, and that growth of vegetation draws down carbon dioxide. But there's also human beings emitting carbon dioxide, and so in the wintertime you get the reverse effect that goes on. The difference between the two annually is the net amount of carbon dioxide that's pushed into the atmosphere. Now, for many greenhouse gases, that's kind of okay because it will drop out quite quickly. It has a warming effect, of course, on the planet, but it doesn't necessarily hang around in the atmosphere. That's not true of carbon dioxide. There is a cumulative effect that goes on with carbon dioxide, and it takes quite a long time, decades, centuries, millennia, for the carbon dioxide to naturally drop out of the atmosphere. And so that's why in any 1 year, if you have an increase in carbon dioxide concentrations into the atmosphere, it's added to in the previous year and then added to in the next year and so on. And that's why the carbon dioxide levels keep going up, even though humans are only adding quite a little bit of carbon dioxide in the atmosphere, relatively speaking. It's a cumulative effect that's causing the damage. Now, that cumulative effect has taken us from 320 parts per million, round about when I was born, to 420 parts per million. That is 100 parts per million in about 50 years. And remember, I told you that the Ice Age did that. We put 100 in the world, naturally contributed 100 parts per million of carbon dioxide from 10,000 years, from 20,000 years ago to 10,000 years ago to come out of the Ice Age. We're doing the same thing, but we're doing it in 50 years. That's 200 times quicker than the world naturally did it at the end of the Ice Age. The other thing to notice about this is that the steepness of this curve is going up. We are putting more and more carbon dioxide into the atmosphere. The problem's getting worse, not better. So despite all you hear about plans for net zero, about reducing carbon dioxide emissions, about the Paris Climate Agreement, COP26 in Glasgow coming up, it hasn't really made much difference. The world is still emitting far too much carbon dioxide at an increasing level as well. It's something we absolutely need to stop, and for reasons which I'll explain. So the carbon dioxide concentration in the atmosphere is over 400 parts per million. And we might ask ourselves, well, when was the last time that happened? When did the world last have 400 parts per million of carbon dioxide? And you've got to go back, unfortunately, before the ice core record. We have no ice that's older than about 1 million years on the planet. You've got to go back a long way into the past, into the rock record, into geology, into a period known as the Pliocene, somewhere between about 5 million and 3.5 million years ago. Then, this is what the planet looked like, then the temperatures on the planet were about 3 or 4 degrees warmer than they are today, and the sea level globally was around about 20 meters higher than it is today. The problem is, if we keep this curve going and we simply get a ruler out and we extrapolate it to 2100, the end of this century, it's possible that there could be somewhere between 800 and 1,000 parts per million of carbon dioxide in the atmosphere. It's completely possible. We might ask ourselves, when was the last time the Earth had 800 to 1,000 parts per million of carbon dioxide? But you've got to go back a long way into the geological record, 55 million years ago, to the Paleocene-Eocene thermal maximum. This is a bit of a spike in the climate at this time, caused by a lot of volcanic activity. And geologically, it looks like a very rapid spike. Actually, it took somewhere between 20,000 and 50,000 years to go from the low hundreds to 1,000 parts per million because of all that volcanic activity. But geologically, it looks instant. The problem is we could do it in 80 years. And again, 200 times quicker than the world did it naturally, even though it looked instant geologically. And actually, when you think about it, what could cause the carbon dioxide values on the planet to increase so quickly from 300 to 400 parts per million in 50 years, and from maybe 400 to 800 parts per million in 80 years? Is there a natural way to do that? The answer is no, there isn't, apart from possibly an asteroid strike. So, you know, in many thousands of years to come, and in millions of years to come, when you look back on this time and we start thinking about the atmospheric composition of the gases that we are responsible for, the only analogy those that come after us might have about this time is it's a self-inflicted asteroid strike, which actually doesn't make any sense at all, does it? Antarctica today is, of course, a beautiful, pristine place, but 55 million years ago, there was no ice on the planet at all, and Antarctica would have been covered by beech trees and beautiful trees. And we know that from evidence in the fossil record, of course. This is a complicated graph, but I just want to labour the point that this is where we're headed. These are the representative carbon pathways of the Intergovernmental Panel on Climate Change, and various ones. The one I'm talking about is RCP 8.5, where we simply burn fossil fuels unabated, which is kind of still what we're doing. The point is that you've got to go back a long way. These are the x-axis here is a logarithmic curve going back millions of years, hundreds of millions of years, and you've got to go back to 200 million years or so before you get to anything like 2,000 parts per million. And again, we could reach 2,000 parts per million in the next century. So, you know, these are strange times. We know the planet will be warming as a consequence of this a lot, and we know we can do something about it. But at the moment, we don't seem to be capable or able to make that decision. So let's make some facts and figures about the world that surrounds us and Antarctica and how it's changing. I want you to have this in your mind. Think about it. How much ice do you think is on the planet today? We know it's melting and the sea levels are going up. So in terms of sea level equivalent volume of ice, if all the ice melted, how much would the sea level go up globally? And you've got an idea in your mind. Just think about that. The answer is about 66 meters. That's the potential sea level rise that exists on our planet right now. So we're going to melt 300,000 glaciers. That's all the glaciers on the planet, apart from the Greenland and Antarctic ice sheets. We're going to melt all those glaciers. And of course, the sea level is going to go up. But my question to you is, how much is that sea level going to go up if all the glaciers all around the world, the entire ice in the Himalaya, the Alps, Patagonia, Svalbard, Canadian Arctic, all that ice goes, sea level goes up, but by how much? And the answer to that is about 35 centimeters. And that tells us that by far the largest store of ice on the planet is the polar ice sheets. And while we are worried about glaciers around the world contributing to sea level rise, and indeed they are contributing significantly to sea level rise, it's the polar ice sheets that could do the big damage this century and next century and beyond. if we don't mend our ways. Now, the last ice age was 20,000 years ago. And of course, there were big ice sheets over North America, over Scandinavia, United Kingdom, Patagonia, many places. And the sea level was lower as a consequence because the water essentially evaporated from the ocean. It fell as snow on the continents. It was held in the glaciers and ice sheets there. The sea level went down, the ice sheets built up. But how much lower was sea level 20,000 years ago compared to today? Remember, 20,000 years ago isn't very long. It's not really geological time at all. It's really just very recently. The answer to that is 130 meters. That means that sea level rose by 130 meters between about 20,000 years ago and 10,000 years ago at a rate of about 1.3 meters every century because of carbon dioxide going up by 100 parts per million. That's what we have to understand. You know, I do this talk to various people, various audiences, and what I like to do is to get you to imagine yourself on your favorite beach and think about you being there right now, and you're looking out to sea. What is it that you're looking at? And of course, everyone says, oh, we're looking at the ocean, it's beautiful. And actually, to a glaciologist like me, what you're looking at from the surface of the ocean to 130 meters beneath the surface, all around the world, everywhere, is melted ice from the Ice Age. So it's an existential threat to many parts of the world. And indeed, it is to London as well. If 66 meters of sea level rise happened, then London's completely underwater, of course. But that might take some time, and it might be millennia before that sort of thing happens. It doesn't matter because it might be coming anyway, and it might be us that's responsible for it. And so we do have to recognize that. But all you need is a small amount of that change to invoke serious problems for the habitability of London and many, many other cities all around the world where there is trillions of dollars of capital investment held up there. Far, far more, orders of magnitude more investment held in our cities than would be needed to solve this problem, by the way. Now, sea level has been going up since 1870 or so, and we know that because we've been measuring it, and our way that we've been measuring it has improved through time. So while there was quite large error bars in the 19th century around here, there's virtually no error bars in the measurements that we have now. And again, just like the carbon dioxide value that I explained previously, not only is the sea level going up, this is in millimeters, so it's about 20 centimeters of sea level rise since the end of the 19th century. You can see that the rate of change is also going up from about 0.8 millimeters per year, end of the 19th century, to 2 millimeters per year in the middle of the 20th century, to about 3.2 millimeters per year around about now. Actually, now it's more like 3.4 millimeters per year. So it's getting worse. Why is it getting worse? Well, half of this contribution is because the oceans have got warmer. It's called thermal expansion of the ocean. So roughly about half of it is that. Slightly less than half is the melting of the 300,000 glaciers that I spoke about. And maybe about a tenth is due to the ice sheets melting from Greenland, predominantly Greenland, and starting to Antarctica. But the rate of change that's increasing is as a consequence of glacier activity. The glaciers and the ice sheets, they are now combined a greater contribution of thermal expansion. And as warming continues, that will always be the case. So now initially it was thermal expansion that we were worried about. Now it's the glaciers and the ice sheets. And in particular, in Antarctica, we're really concerned about this because the Antarctic ice sheet is losing mass in the last 30 years. 6 times more mass is being lost today than it was in 1990 at the start of the satellite record. And it's parts of Antarctica that we are particularly worried about. This is the West Antarctic ice sheet over here. This is a satellite altimetric change map. So this is the surface elevation of the ice sheet. And if it's white, that means there's no change. If it's blue, it means the ice surface has gone up a little bit. And if it's red, it means the ice surface has gone down. And it's the grounded ice around West Antarctica and indeed in bits of East Antarctica that we are really worried about. There's enough ice here to raise sea level by many tens of meters, and it's starting to get mobilized. And this is why we're worried, because the West Antarctic ice sheet isn't resting on land above the level of the ocean. It's resting on land continent that is below the level of the ocean. And as is parts of East Antarctica, in fact, the bits in red you can see there, correlates with the bits of the land underneath the ice sheet that is below the level of the sea. And that's really worrying because it's ocean warmth that's doing the damage to the ice sheet, not atmospheric warmth. Particularly worrying because ocean warming can melt glaciers at around about 10 times the rate that the surface air temperatures can. Very cold in Antarctica. There is melting, but there's not a lot. Most of this melting, the vast majority, is due to ocean warming, and that's why we're concerned about it. Not only that, because this glacier is resting on a bed that is sloping inwards towards the continent of the ice. So as I'm telling you that the ocean is doing more damage, as the ice sheet retreats, that grounding line that separates the grounded ice from the floating ice is going into deeper and deeper land. And that's going to have a feedback process that accelerates the rate of ice loss. It's called marine ice sheet instability. And there are some people, some glaciologists, that think it's already started in West Antarctica. If we knew nothing about the fate of the Antarctic ice sheet, and we were just to assume hypothetically where the West Antarctic ice sheet would disintegrate itself, where that would start from, it actually would be here. This is exactly how we would anticipate the West Antarctic ice sheet collapsing. And indeed, that is where we're seeing measurements of that change right now. So we're very worried. In East Antarctica, although there are parts of East Antarctica that are resting on land, which is quite way above the level of the ocean, and it would take atmospheric warmth to melt that, which we're not particularly worried about, there are still 10, maybe 20 meters worth of global sea level rise held up on the ice in East Antarctica that is currently resting on a bed below the level of the ocean. And again, it's ocean warmth that's going to cause this problem. So the Intergovernmental Panel on Climate Change did an assessment 5 or 6 or so years ago, where they looked at 3 scenarios for Antarctica and Greenland. You know, a worst case scenario where there's a lot of melting, a best case scenario where there's not too much melting, intermediate. But since then, we've been able to put on observations over the top of these projections. And what I can tell you is that the projections are mostly in line with the observations. That's the observations are tracking the worst case scenario.
Martin, we can't hear you.
Yeah, sure.
How long have you not been able to hear me for? Can you hear me now?
Just now. Just now.
Okay. So as I said, I'm a glaciologist, and I have been studying the Antarctic ice sheet, and I can do a very similar problem, an explanation for heat waves. There have been tremendous heat waves around the world the last few weeks that we've all known about. And that is going to get worse. You know, we have an opportunity to cap emissions and keep global temperatures below 2 degrees centigrade. But we're still going to have more heat waves. But if we don't do that, and global temperatures go in excess of 5 degrees centigrade this century, and then beyond it, the world is going to be uninhabitable in many places. Similarly, with croplands, we're not able to grow enough food to keep ourselves going because of what we're doing, the damage we're doing to the planet. Similarly, with flooding, again, flooding that's been observed in Western Europe in this last week has been appalling. No one has ever seen that type of flooding. And unfortunately, it is going to get worse. We are already locked in to more changes. The question is, can we restrict how bad those changes are going to be in future? And we can do that by reducing carbon dioxide emissions urgently and immediately. But unfortunately, the pathway we're on is essentially to no mitigation at all. And in particular, we're worried about water. This is because we're overusing fresh water in aquifers beneath the surface of the land, which often takes centuries, sometimes millennia to build up. And we're depleting them in many parts around the world much more quickly than they can be replenished. And so our ability to irrigate the land and drink fresh water is going to be severely impacted if we don't mend our ways. So this is the choices that we have. Here we are, we're at 2100, we're at this point here. And these are our futures. They are diverging futures, and they are completely consequent of the decisions that we make right now. Like I told you before, you know, the landscape around the British Isles is a consequence of processes that have been going on before us. They have consequences for later in our future. What we do now will have consequences for our future, and we absolutely know that. Are we going to pull down emissions to zero by the middle of the century and have a world which is, well, unfortunately, less inhabitable than it is today, but much, much better than it will be if we simply do not reduce our carbon dioxide emissions? This is a global emergency. It's something that we know we can take action on. It's something we know is our problem, is our fault. And if we don't, then those who come after us, our children, and the children that come after them and so on, will look back on this time with anger and disappointment that we knew we were doing something bad to the planet. We knew we could change our ways, but we chose not to. This is our problem and we need to solve it. A problem that we've got here, we did some work for the UK government a short while ago that said, if we take action, global action on carbon emissions, and we do it now, it will cost us about 1.7% of gross domestic product globally. Slightly less for the UK actually, but yeah, that's how it is. But globally about 1.7%. And we have to decarbonize at around about 4% per year. That's what Sweden did in the 1970s to decarbonize its power supply, for example. So we know we can do it. And we need to deploy these technologies at rates that we know we can. But if we leave it 10 years, just 10 years, in fact, these 10 years that we're now in to 2030, then we have to add another 0.5% of global gross domestic products. We have to decarbonize at rates that we've never done before, and we have to deploy technologies at rates that we've never done before. So this is not something we can park into the future. This is not something we can say, well, it's going to be difficult. We're going to start it in 10 years' time. It's going to be far more difficult to start it in 10 years' time, maybe impossible. It's going to cost much more money if we started in 10 years' time. The best time to have done this was 20 years ago, when it would have been, frankly, quite easy to have done it. But we didn't take that opportunity despite the science saying that we should. So we need to understand that this is going to get a lot worse if we don't take action now, that there is an investment that's needed, but it is urgent, and we are responsible for doing it. So let me leave you with this beautiful picture of the surface of some mountains poking through the ice in Antarctica. And just to say that I, and many people, would like to leave this place in this pristine condition. I would not like to see this deglaciated. If this deglaciates, the world is going to have consequences for it. And I want to point also out this picture. This is my son, and this is a holiday photo that we took when we were in Suffolk last year, and he has got his hand on a glacial boulder. This came from Norway 500,000 years ago. It came from Norway 500,000 years ago because the carbon dioxide concentration went down from 280 parts per million down to 100 parts per million, 180 parts per million. That is what 100 parts per million of carbon dioxide can do to the natural world. We are putting in far more than that at the moment. And if we don't mend our ways, the world is going to see many, many more changes than just boulder side investigation. Thank you very much. I'll stop there.
Thank you, Martin. There is
Thank
time.
you.
Yes, sure, sir.
Thank you very much, Professor Martin. It was really fascinating talk, and I'm sure that there will be many questions and discussion. So I request Naresh to moderate the discussion. Naresh, over to you.
Thank you, sir. Thank you, sir. So Martin has talked about the consequences of what we are practicing today. I am sure there will be reactions and questions from this audience. If there are questions, please unmute yourself and ask that, or you can put also in the chat box, whichever way you would like to do. But you can directly ask the questions also. Please raise your hand so it will be easier to Okay, yes, I see a hand actually. Will you please ask the question?
Yeah, Martin, thank you so much for a wonderful talk. I have a very small question. We talked about the West Antarctic, but your research on ice cap and Professor Pant as well speaks about the changes happening in East Antarctica. Could you throw some light on what is happening in East Antarctica and what do you foresee in decades to come?
Yes. So in West Antarctica, we know a lot about Thwaites Glacier and Pine Island Glacier. These are the big glaciers that are losing mass at the moment. But in East Antarctica, it's often been overlooked, actually, as being a part of the ice sheet that is changing. But we know that it is, and the satellite records tell us that. What the ice cap program did nearly 10 years ago now was chart the land underneath a place called Totten Glacier in East Antarctica. And what we showed there is that the land, just like in West Antarctica, the land slips away, gets much, much deeper toward the center of the ice sheet than it does. We also showed that there is a channel on the continental shelf that allows quite intermediate warm water offshore from Antarctica to seep in and advect itself through to the ice sheet edge. So that's what you need. I mean, there's a number of things that you need to cause the ice sheet to start melting. Somehow the ocean warmth alone is not enough. You need that warmth to be able to be in contact with the ice. And so the landscape underneath the water and the ice is either going to allow that to happen or not allow it to happen. And if you have essentially dikes and sills and walls and things that are going to prevent that deep water, or if the continental shelf is shallow, then it won't happen. But in Totten Glacier, and of course in Pine Island and Thwaites Glaciers, that's not the case. There are deep troughs that allow that water to come in and to lap against the ice edge. And although it's quite complicated at Totten Glacier, we demonstrated how it can happen. And since then, there have been measurements of the water demonstrating that is actually what happens. Now, the open question is, of course, as the glacier starts to recede and the distance between the continental shelf and the ice grounding line gets increased, how does that heat supply continue? Because once you start to melt the ice, you know, it gets quite cold. You need to keep replenishing it. And what happens underneath the floating ice shelves becomes really important here. Do you get the constant influx of warm water and a constant outflowing of cold water as a consequence of the melting? And if you have an efficient process by which that happens, then you can continually melt the ice grounding line. And that's why we need to have many, many more observations about the oceanography underneath the floating ice shelves, because it's an area of investigation that we need much more knowledge about. In many parts of Antarctica, Greenland especially, but in particular in Antarctica, you know, the ocean conditions underneath the floating ice shelves are critical to how the ice sheet is going to behave. And yet our observations are really sparse. And so that's something we do need to improve.
Thank you.
Yes. Till such time there are other questions, Martin, I will probably ask something. When we look at the big picture and we use a word threshold, and when we talk about, let us say, Arctic, I believe that we can say the threshold is crossed. Now, what is the position of science, or in context of science, what is that we can do to estimate thresholds in Antarctica in different domains?
It's a really good point. And scientifically, it's an area of investigation that we've been thinking about for several decades, of course. The idea of there being tipping points, or a threshold at which afterwards there's a different state to what we have before it. And hypothetically in science that it's kind of known. We have this type of behavior in many areas of science. But in the natural world, we have to think about it. There are a number of feedback processes that we're absolutely certain is going on. I mean, the Arctic is warming at a rate of about 3 times the average of the rest of the planet. And the reason it's warming so quickly is because the sea ice is melting away, and that white reflective surface is being replaced by a dark surface that absorbs solar radiation rather than reflects solar radiation. So the more sea ice, the warmer the world gets, the more the sea ice retreats, and then the more the Earth absorbs the solar radiation because the white surface is no longer there, and then the world warms even further, and it's a feedback process. Whether there is a threshold at which actually the whole thing just goes away is a moot point. And I think it's fair to say that this is a real concern in natural science, but it isn't something that we have a really good handle on. And it's not something we can say 2 degrees centigrade, 1 degree centigrade more than it was in we were already 1.2 degrees warmer than we were in 1850, pre-industrialization. And so when we talk about 2 degrees centigrade, we're actually just referring to 0.8 of a degree centigrade. Is that a tipping point? Well, you can argue we don't want to test that. That's like an experiment that we do not want to conduct. But it's fair to say also that we don't know. We absolutely don't know. I would argue we don't want to know and best stay away from it. But is it actually a tipping point? I'm not so certain. Certainly, if we can regard the world as essentially having a cooling system. The snow and ice around the planet reflects the sunlight and essentially keeps us cool. The oceans absorb a lot of the atmospheric heat and essentially keeps the atmosphere cool. But if that doesn't happen anymore because the snow and ice melts, and then you get excess warming and the oceans can't absorb any more heat, then what happens then to the planet? You have a runaway effect and the planet stops cooling itself and actually starts heating itself. And we know that can happen. We know naturally the world can heat itself naturally, and we're encouraging it. One thing I would say is that Milankovitch and Kroll were right. Ice ages are caused by orbital variations, but they are just nudging the system. They are just putting small changes into the Earth system that then gets adopted by processes that are responsible for carbon dioxide increasing or decreasing, and that's really all about the oceans. And it's that does the damage. We are not nudging the system. We are smashing it with a sledgehammer at the moment, much, much more than an orbital variation might do. And so, you can argue very strongly that we already caused a tipping point. And that tipping point started in 1850 when we started burning fossil fuels at an industrial level. Because as I said, the only geological analogy that we have to what we've done isn't a volcano or anything like that. It's an asteroid strike.
Thank you. I think that's a fair bit of warning. Our veteran Antarctican Dr. Rasik Ravindra wants to ask you a question.
Hi.
Yeah, thank you, Martin. It was a very interesting talk. I just have one small observation. Well, we all know that if we keep on increasing carbon emission, there's going to be a global warming and global emergency, as you have said. But the problem is that the developing world, it does require energy, and it has to burn fuel to keep on progressing. So how to drive a balance between the development and between the reduction of the carbon emission? Can you suggest something for the policymakers?
Yes, thank you. And that is really one of the most important problems that we need to face, isn't it? I mean, developing economies, goes hand in hand with the development and growth of middle classes, and that goes hand in hand with consumption, and we're consuming more. The sort of the way that we live in the United Kingdom, if you just replicated that billions of times around the world, that's unsustainable. The planet, we cannot live in that way. And so what we need to craft is a low/zero carbon way of living on the planet that allows us to have fulfilled lives, to be happy. And what I would argue is that we are fed information to convince us that we're happy, But actually, when you look around us, our air that we breathe is filthy, that we're dying as a consequence of it. Our streets are full of traffic. We're not actually living very healthy or happy lives, but we are being convinced by vested interests and other companies that that's what we should aspire to, and it's nonsense. There's another way to live, of course, in a way that is completely compliant with growth of middle classes and consuming things, but we do it in a responsible way. We have got a lot of things to do in terms of developing a circular economy rather than throwing things away, reusing things. We've got a lot of things to do in terms of taking out fossil fuels and replacing them with renewable energy sources, which is completely possible to do, by the way. That the reduction in the cost of wind and solar electricity over the last 10 years has been remarkable, and that's always going to go in one direction. And it's already cheaper than generating electricity from oil and gas, but it has the added benefit that it doesn't pollute the atmosphere as well. Our solution to this, I think, is going to come if we recognize the economics of this problem in an appropriate way. At the moment, you can burn things into the atmosphere, you can pollute the atmosphere. We know it has a cost because we will pay for it in human lives, and people that are going to be after us are going to pay for it in climate change. But we don't pay the price of it now. We don't factor it in. And if we started to do that, if we started to actually recognize that we need to pay the full cost of that pollutant, the polluter pays, then it changes the economic playing field completely. And we can start investing wholesale in renewable energies in a way that, because fossil fuel equivalents will be uncompetitive. Now, we have to recognize that as being the solution, and then we have to understand, well, why is it, if it's so obvious that's the solution, why are we being held back? And unfortunately, we're being held back because of vested interests. We're being held back because oil and gas companies have got such a stranglehold on the economy right now. The question is, can we trust oil and gas companies to transition themselves away from this monopoly that they have at the moment over our society to, in 30 years' time, being absent? Can we trust them to do it? And I would argue there's nothing that they've done over the last 30, 50, 100 years that would allow us to trust them at all to do this transition. And we need to work much more seriously on this and not expect oil and gas companies to do it themselves. Now, they are part of the transition, and I don't want to demonize oil and gas companies, and they have really, really important roles to play. They've got amazing expertise. You know, offshore floating wind farms are completely in line with a net zero outcome, and oil and gas companies have amazing expertise and experience of doing that sort of thing. But they need to channel much more of their efforts into that type of technology than they are at the moment. They need to stop exploring for more oil and gas fields, because we know what all the oil and gas is. I mean, it's a crazy, I mean, a lot of geologists here, like Naresh, I'm sure. It's a bizarre thing that oil and gas fields and coal seams are essentially carbon dioxide that was once in the atmosphere, drawn down by plants and trees and animals, buried underground for millions of years, stored underground for millions of years. And what we've been doing in the last 100 years is digging them up, burning it, and putting that carbon dioxide back into the atmosphere. At an industrial level, we could not, if we wanted to warm the planet, if that was our intention, we couldn't have done it more quickly than we've done it. And we need to recognize that. And the reason for that is because of burning fossil fuels. There's a lot of money around in fossil fuels. There's a lot of people making a lot of money in fossil fuels right now. And there's a lot of vested interests, which is causing inertia. And as I said, it's that inertia that we need to recognize and understand is in the way of our progress. And we need to do something about it. Personally, I think oil and gas companies need to be, especially the state-owned oil and gas companies, probably need to be broken up into their different sectors. So you have an opportunity to invest in the parts of those companies that are contributing to renewable energy, for example. But at the moment, you can't do that. If you wanted to invest in Shell, for example, you invest in Shell, not Shell Renewables. But if there was such a thing as Shell Renewables, and it had an investment opportunity, you see the investments flooding into that. And you would see no investments going into Shell exploration. And until the oil companies recognize that, we're not going to see the progress that we need. Sorry, Ritik, that was a big answer too. I'm not sure the question that you asked me actually, but I went off. Sorry.
Thank you. Thank you. That was quite convincing.
Okay, are there any other question? Oh, yes.
Dr. Pant,
Yeah.
this is Dr. Ramani from Penn State.
Yeah, please. Please go ahead.
Yeah.
Can I request others to mute their mic, please?
The question for Martin is coming from an engineer and one who is involved in natural resource extraction and the inevitability of natural resource extraction for construction and other human activities, and recognizing that the whole process involves a certain efficiency. Work cannot be done at 100% efficiency. What are we trying to do in all these conservation processes from a geologist's point of view?
It's a really, really good question. Engineering, I mean, I talked to my son about what he might want to do. You know, he's 12 years old, and what he might want to do in his time, and I'm trying to convince him to be an engineer, because we need engineers to face this problem. We can design the future with engineering, with new technology, deployment of that technology. But there are some things we can think about. You know, I talked about the circular economy, reusing things rather than throwing things away. That's important. But you're absolutely right. There will still be raw materials that are going to be needed. Of course they are. But there will be ways in which we can offset those emissions. And I'm absolutely convinced that direct air capture of carbon dioxide is going to be something that we will need to deploy at scale to make a difference. I'm absolutely convinced by that. I'm not at all convinced by biofuels. Just doesn't scale. I mean, it might make a contribution of a few percent, but it won't scale in the way that we need it. Building materials, cement and steel. We're actually developing in our Clean Tech Accelerator program a company that has perfected a recipe for zero carbon cement. It can be done. And working with Arup, the construction company, on seeing if that can be scaled. I mean, the problems with these sort of things are you have a recipe that works, but is it robust in 50 years and 100 years or whatever? And these are the sort of things that we need to work out. The natural world is our friend, right? And we need to treat it as a friend, not as an enemy. The Amazon forest is an amazing place, and we need to recognize that it has a value. It has an economic value to our planet. And if we don't regard it in an economic sense, then, you know, we treat it in the way that it is. One of the reasons, you know, we need to live on this planet. We pay for everything that we need to live. We pay for water, we pay for food. The only thing we don't pay for is the air we breathe. We don't pay for that. And it so happens that it's the air that we breathe that's the most polluted. It seems because it's for free, we don't care about it. And that, of course, is not correct. You know, we need to work on these problems. We need to think about natural solutions regarding the natural environment as being a place that we need to preserve, with biodiversity parts of this as well. But as to answer your question, you know, we shouldn't be scared of the future. We shouldn't be daunted in a way that paralyzes our decisions. We should recognize that there are solutions already, and we need to deploy them, and with greater talent facing this. And I'm absolutely convinced when I speak to young people, they're really passionate about this. With deploying that talent to face this problem, their careers, you know, the 30 years that are coming are going to have to be decarbonized. And that is essentially going to be the careers of kids at university now, right? This is their career that we're talking about. We need to power them up with the skills, with the ideas to make the difference. And that's our challenge. That's what we all have to do right now. Is that we've caused a lot of this problem, but if we don't hand it over to the next generation as a solution, as an opportunity, I fear we're failing.
Thank you very much.
Thank you, Martin. I recall Professor Raja Ramani from Penn State asked this question, and I recall from his lecture, he's a mining engineer, and he said that mining actually is nothing but a change in land use pattern. That the approach to mining has to be a change in land use pattern, And that was the most striking message from his talk last March.
Thank you. It's a really good point. Yes.
That's an excellent point which he made. I see another question. I see another hand raised. I'm sorry, I'm not able to see the name. Will you please
Dr.
ask?
Verma. Dr. Verma.
Oh, Dr. Verma, please. You have to unmute yourself, Dr. Verma. We can't hear you. Verma sir, we can't hear you.
Professor Pant, I think it is Dr. Partha Sarathi who wants to ask the question.
Okay.
Hello. I just want to find out the possible effect of worldwide yearly bushfires on global warming.
Yes. I don't know the answer to that, actually. I'm not sure what the percentage contributions are going to be. It can't help. There's a number of things to talk about the bushfire. Firstly, they're awful. And the wildfires, we're talking about human lives, human livelihoods, scorching heat over many. But what's happening in California at the moment is just appalling, of course. And they will make a contribution to greenhouse gases, absolutely. I don't know what the percentages are, unfortunately. But what I would also say is that often you hear about offsetting carbon through growing trees, and absolutely nothing wrong with putting trees in. That's a really good idea, as long as they're the appropriate trees for the place. What we don't hear much about is what happens in the situation where you might have a forest planted for that purpose that then burns down. I mean, offsetting generally is something which you offset, and it takes some time to do it. And I'm particularly worried about the stability of offset forests in a situation where we expect more forest fires to occur. I mean, essentially, I talked about it previously. Direct air capture of carbon dioxide seems to me to be a necessary thing that we are going to have to do at scale to do proper offsetting, and then also to draw down carbon dioxide. And if there was an economic price on carbon, it would make all the difference. And that's another thing that we really absolutely need to do, is the economy of climate change is completely unfair. If you design the economy the way it is, you simply arrive at the situation that we found ourselves in, and it's not fair. We need to start recognizing the economic cost of the damage, factoring that in, recognizing that carbon dioxide and carbon should have a price, and if it did, it'd make a big difference. Forests and offsetting are going to be important for sure, but I don't think they're the end. And I'm just like you, I'm staggered, I'm appalled by the amount of forest fires that we're seeing, and it takes it will inject carbon dioxide, certainly will, but unfortunately I don't know what the numbers are for that.
Thank you. If there are no other questions, are there any other questions?
Sir, I have one question. I am Lamarov.
Please.
When is the next ice age expected, sir?
Yeah, it's a good question. So it should happen in about 10,000 years, but only if carbon dioxide levels were something like about 280 parts per million. And then the world would naturally come down that way, but they're not. They're much higher than that. They're at 420, 415 parts per million. And there was a paper that was done a couple of years ago by a colleague of mine in Germany, John Schellenhuber, who, with some others, concluded kind of what we knew already, that it was not possible for the ice age, the next ice age, to happen as a consequence of the carbon dioxide level just simply being too high for it. So you could argue that we've already changed our future, that we will not have another ice age. These happened over a long period. It takes tens of thousands of years to get into an ice age. So that's that. But it's staggering to think that we've had such a profound effect on our planet in such a short amount of time. but that's it. The answer is we can't have another one until the carbon dioxide level comes down.
I had a question for Martin.
Please.
Martin, just about, I think it was 40 years ago, I guess 1980, Time magazine had a cover page coming next to Ice Age. And
yes.
Talked about and the question is, do we know what we are doing really?
Yeah, absolutely. So let me I'm going to share my screen again, and I'll take you back, because you're absolutely right. There was a lot of discussion about. There's a lot of discussion about the ice ages in the 1970s, I think, not necessarily 1980, probably a bit earlier than that, and it's because of this graph here. So in the late 1960s, we still didn't really know what caused the ice ages. It's 50 years ago, we didn't know what caused the ice ages. Milankovitch ideas and Kroll's ideas weren't accepted at all because of what I explained. But then the ice core record happened, and also the seafloor sediment record, which is very similar to this. And it showed that the periodicity of this matches exactly with Kroll and Milankovitch. But we didn't really appreciate back in then what the carbon dioxide was doing in the 1960s, because in the 1960s it was only 320 parts per million, not where it is now. And so the idea at the time is that ice ages are happening periodically. We are at this situation here between an ice age. We're due a new one, and we're due it imminently. And of course, that was a good idea. There were many scientists around equally at the same time, and I could point to a very famous paper in Nature magazine in 1978 that looked at the carbon dioxide values, looked at where they were going, and said the West Antarctic ice sheet is in peril because of carbon dioxide warming that's going to happen. But you're absolutely right. In the early 1970s, there was this scientific appreciation that Kroll and Milankovitch were correct, that ice ages are paced by orbital variations, and that we are due a new one. We are due a new one. But actually, science has kind of moved on very swiftly since then to paint a different picture about our future.
Okay. If there are no other questions, Dr. Nayak, can we come to the last part of this, with your permission? Okay. Okay, Martin, I know that you also have engagements, so I will take few minutes to express our collective thanks from the Krishnanunni Memorial Charitable Trust. Krishnanunni was really a visionary who looked at environment in that sense, and you are one of the most appropriate person to talk about what we are doing to ourselves and what is happening to us. In a sense, what you told us, that in which way the human race has actually failed and what possibly we can do to mend that, which is also very tough to do in near future. But it is essential for our next generations. So thanks a lot for an excellent introduction and letting us know that where we are lacking, and hopefully we are able to pass this message to younger and younger people, so that because it matters more to them. So thanks once again from the entire Krishnanunni Memorial Group and Trust. And I also would like to thank our President, Dr. Shailesh Nayak, who actually has made all the arrangements for this meeting and who has taken a lot of care and who takes really personal interest in these things. And Sri Parthsarthi, who is untiring at his age, untiring soldier in pursuing the aims and objectives of the trust. We from the trust are also thankful to the memorial group members, NCPR, and all other people who have attended today's talk. Once again, thanks, Martin. And we hope that we have more interactions in future. Thank you. Bye. Okay, bye.
Hello. Hello.
So, Professor Satyasab, it was good. It was a good lecture.
It was excellent. I think the added attraction to the lecture is participation of Unisab's sisters in this
That's
lecture.
good.
And then much more important was the participation of 80 plus year old young man, Professor Venkatramani. It is early morning today, and he still took the trouble of getting up and then participating in this one. I thank him for joining this group, this talk.
I don't know if he's listening.
I hope so.
No, it's I appreciated the lecture, and I thought it was wonderful. Being interested in generally in climate change and the welfare of the society in coming years, and as you know, and for materials that causes all these increase in heat in the environment. Whatever is not efficiently used is what is left behind as heat that increases the temperature. And therefore, the question really is, how can we do things more efficiently? And that was my question. My question in general, but engineers have probably the greatest responsibility here to do things more efficiently, not waste resources, more effectively, because we will continue to need the resources. If you tell me that I have to sacrifice my way of life to improve society's conditions, you are not going to find anybody in society agreeing with you to sacrifice their way of life. Impossible. And that means as engineers, we have to do it despite that desire and find more and more effective and efficient ways. So I appreciated the invitation, enjoyed the lecture, was very, very well-meaning lecture. And as you know, Penn State is one of the very leading educational institution on the subject of global